Today's lab is on Newton's second law, which is probably more familiar of all of Newton's laws. And Newton's second law says that if an object is accelerating, the sum of the forces on the object is equal to the mass times the acceleration. So another way of looking at it is that if we have an imbalance in the forces, then the forces are going to be responsible for accelerating that mass and moving it. So if an object is at rest and then someone applies an external force to that object and starts pushing that object will move from not moving to moving. It will accelerate. It will change its velocity from being at rest to being in motion. So the idea is pretty simple. The sum of the forces are equal to the mass times the acceleration, right there. So how are we going to study it in the lab today? We're going to do it with something called the Atwood machine. So an Atwood machine is a very simple device. It is a pulley wheel with two masses, mass 1 and mass 2. And we want to have the masses to be different. Say mass 1 is heavier than mass 2. So that mass 1 will then accelerate downward and mass 2 will accelerate upward. So therefore both masses are going to be accelerating. They're actually going to be accelerating at the same value, just in different directions. And the reason they have the same value is they're connected by a string. And so we essentially have mass 1 connected to a string, run over a pulley, connected to mass 2. So if we analyze it using Newton's second law, then looking at mass 1, so the force diagram has the tension of the string pulling the mass up, the weight of the mass pulling it down, and there is an overall acceleration downward. And so the sum of the forces are the tension minus the weight is equal to minus the mass 1 times the acceleration. Then if we analyze mass number 2 has the tension again pulling it upward, its weight pulling it downward, but now mass 2 being lighter is accelerated upward. So now the sum of the forces is the tension minus the weight, m2g, equal to m2 times a positive acceleration. So if we take these two equations, substitute out the tension, and then solve for the acceleration, you get a very nice formula, which is the acceleration of the masses is equal to the acceleration due to gravity, g. In this case, we're on Earth, so it's 9.81 meters per second squared. But it's g times the difference in the masses, m1 minus m2, divided by the sum of the masses, m1 plus m2. So you have this ratio of the masses, which now gives us the value of the acceleration, which is some factor of g. So with this, we're going to measure g. So we're going to implement Newton's second law, measure the acceleration, and then extract the value for g. So you can ask, how are we going to measure the acceleration? Well, we're going to take advantage of kinematics. So if I look at this diagram of the Atwood machine, m1 is some distance above the ground. So that distance I'm going to call x, and using the kinematic equation, the final position of mass 1 is equal to its initial position plus its initial velocity times the time, plus 1/2 times the acceleration times the time squared. Again, if we say that its initial position is 0, its initial velocity is 0 because I'm releasing it from rest, then therefore the distance traveled is just 1/2 the acceleration times the time squared. So you can now calculate the acceleration as 2 times the distance traveled divided by the time squared. And that's what we're going to do today. So what I've built here is an Atwood machine. So it has a pulley. It actually has 2 pulleys, but that's okay. They're both achieving the same action, which is to have, essentially a pulley system the masses can move up and down across. You probably can't see it because it's a very thin string, but I have a string, and connected to this string is mass number 2, the lighter mass, And on this side is mass number 1, the heavier mass. So what we're going to do is we're going to start with the heavier mass up in the air, and we're going to measure its distance that it's going to travel. So that is 91.5 centimeters. So 91.5 centimeters is the distance x. And then we're going to measure the time it takes for the mass to fall, that distance, use that time and the distance to calculate the acceleration, and then you're halfway there. So what I'm going to do is I'm going to pick 5 different sets of masses. So let's say that mass 1 is always going to be 200 grams. So mass 1 is going to be 0.2 kilograms. And then what I'll do is I'll start with mass number 1 being at 0.15 kilograms, 150 grams, measure the time, and then I'll measure that time 3 times. So we'll repeat that measurement thrice in order to get an average value for the time. And then I'll move on to 160 grams, measure 3 times for it to fall, and then go on to 170, 180, 190 grams. And so we should have 5 data points with which to put on our graph. And I'll explain the graph after we take the measurements. So let's start with 150 grams. So mass 2 is 150 grams. And mass 1 I said was 200 grams. And let me get my stopwatch going. And so I said we're going to measure these 3 times in order to take the average. And so ready, set, go. Okay. So the first time is 0.96 seconds. So let's do this again. Ready, set, go. So this next one is 0.110, so 0.11 seconds. And the last one, ready, set, go. 0.103 seconds. So 0.103 seconds. Okay. So that was at 150 grams. Now we're going to move on to the next one. I'll add 10 grams to it. So I'll make that 160 grams. Be careful for the falling meter stick. Okay, so let's do this. So 160 grams, time number 1, ready, set, go. 1.22 seconds. Okay, let's measure it again. Ready, set, go. Okay, let's try that one more time. Ready, set, go. Okay, 1.30 seconds. Okay, and now the third time for 160 grams. Ready, set, go. 1.29 seconds. Okay, so now let's go up to 170 grams. Okay, ready, set, go. So 1.80 seconds. Okay, ready, set, go. Okay, that was 1.46 seconds. So a little bit of variation there, but we'll keep it. And now ready, set, go. 1.55 seconds. Okay, so a little bit of a spread at 170 grams, but we'll keep it. Okay, so now we'll add 10 more grams and we'll measure at 180. Okay, ready, set, go. Okay, 2.25 seconds. Okay, try it again. Ready, set, go. Let me try that again. Ready, set, go. Okay, 2.33 seconds. And the last time. Ready, set, go. 2.19 seconds. Okay, and our last measurement now is at 190 grams. Okay, ready, set, go. Okay, 4.06 seconds. Let's try that again. Ready, set, go. Okay, 3.69 seconds. Okay, let's try this again. Ready, set, go. Okay, 3.86 seconds. Okay. So I think that's as far as we want to go with the measurements. I think at this point the acceleration would be so small. If we added more mass, the acceleration would be so small that it wouldn't be able to overcome, say, the friction in the axles of the pulley. So what I want to do now is just share the measurements. So here is our data. So what I'm showing is the mass 1, the heavier mass, which is 200 grams. Mass 2, which was our variable, which went from 150 to 190 grams. And then the 3 times that we had for each of those sets of values. For every measurement, the distance that was traveled was 91.5 centimeters. And so what I want you to do is to average the times, get an average time for each set of masses, calculate the acceleration from kinematics, and then make a plot of the difference in the masses divided by the sum of the masses, and then plot that against the acceleration, and you should get a linear plot. And from the equation at the beginning of this video, then you should be able to extract the slope, which is 9.81 meters per second squared, or, hopefully close to that value. So this is the summary of what you're doing. Use the times to calculate the accelerations, plot the measured acceleration versus the ratio of these masses, the ratio of the difference in the masses to the sum of the masses, plot it with a line, and extract G from there. So, good luck.